Okay, in this video we're going to go over our review before the first test of this semester in calculus. Now if you recall, this test will cover three things: the difference quotient, the idea of limits, and then finally continuity. So we'll see how much we can cover in this particular video, and I'll record a second as needed. Now at the beginning here, this particular question is asking us to find the instantaneous rate of change of a function at a given value. And it says that you may use the provided graph to sketch the function. That was a mistake that I made while building this worksheet. I meant to actually provide a picture of this graph so that you can look at it, but that's okay. This is a sketch of what the graph would look like. It doesn't have to be perfect here because I just want to use this as reference when we compute our instantaneous rate of change. So we would like to know what's the rate of change when x is equal to 0. That's what's implied here. When x is equal to 0, what's the instantaneous rate of change? Now this vertex is somewhere to the left of 0 on the x-axis. So to me it looks like we are increasing at this point. It looks like there's a positive slope at that particular spot. So when we're done here, we would expect to see a positive result for the instantaneous rate of change. Now if you recall, instantaneous rate of change will be the slope of a tangent line, and our definition for the slope of the tangent line involves limits and the difference quotient. So this would be the limit as h approaches 0 of f of x plus h minus f of x divided by h. And if we can simplify this expression and either directly substitute or interpret the limit as h approaches 0 of the end result, then we can also substitute an x value of 0 in this case and determine the instantaneous rate of change. So in class I had mentioned how it might be easier to compute your f evaluated at x plus h off to the side, and that's what I'm going to do here. Because to evaluate that I need 2 times x plus h quantity squared plus 2 times x plus h, and then we'll subtract 1 from that. So this looks to me like it's going to be 2x squared plus 4xh plus 2h squared plus 2x plus 2h minus 1. Now back here I distributed and FOILed simultaneously because I've seen this enough now that I can FOIL that in my head and then I can account for the distribution all at the same time. Hopefully you've had enough practice with that too. So as I bring it back to the limit over here for the definition of our tangent line slope, I just copied that over there while I paused the recording. There's my f of x plus h component, and all of that must subtract my f of x component. Now I'm going to kind of bleed over here, but that's okay. Hopefully you've got more room on your notebook paper. So I've just recorded the f of x component and the h component. Now this is pretty nice for us because we see that 2x squared take away 2x squared is going to cancel. We have 2x that's going to take away another 2x and cancel. And whoops, I forgot to copy something from before. There was a minus 1 at the end here. Hopefully you caught that. And this minus 1 take away negative 1 also will cancel. And what we're left with are these terms here. 4xh, 2h squared, and 2h. Now each of those have a common factor h in them. So I had mentioned in class that it's a good idea to factor that out before you try canceling anything. This way you don't accidentally cancel something that you shouldn't, or factor something that you shouldn't. Now we can clearly see that the numerator contains a common factor of h that can factor with the denominator. And we now have the difference quotient for x plus 2h plus 2. And I'm getting sloppy here because I really should include my limit notation every line. So remember, we're not saying that the equation is equivalent each time. We're saying that the limit of the equation or the limit of this function is equivalent at each iteration. So now we're noting that our slope of our tangent line would be equal to this expression as h approaches 0. And so fortunately for us, as h approaches 0, this component tends towards 0, so it essentially disappears. And we can now make note that the slope of any tangent line will be, of this particular equation, will be equal to 4 times x plus 2. And if any of you have seen calculus before, or any of you that are watching know a little bit about calculus, then this answer should look very familiar if you know the rules for computing derivatives by looking at this particular polynomial. I think we're in agreement here. So anyway, we're not quite done. The slope of the tangent line when x is 0, I might just include this here to make it look like a function. Well, that would simply be 4 times 0 plus 2, and 4 times 0 plus 2 is indeed 2. And so we can make the claim that the slope of our tangent line at that point here is a slope of 2. Now here again, my sketch wasn't perfect, but we did recognize that it should be a positive slope, and to make the claim that that slope at that particular point is equal to 2, I think seems pretty reasonable. So I would move on from there. Now I do recommend that you try this example on your own, so please do so and show me what you get. For number 3 and number 4, we have much the same approach. This time I would expect you to do that without referencing a graph. So I don't want you to know what this particular picture looks like, and I do want you to evaluate the slope, or the instantaneous rate of change, when x is equal to 1. Now in example 3, we would do the same thing as before, and off to the side I've determined what f evaluated at x plus h would be. I've made the substitution and simplified it, and I'm bringing that over to the difference quotient. So the slope of our tangent line would be the limit as h approaches 0 of f of x plus h, this component here. Take away f of x here, all divided by h. And as we distill that down and simplify and determine the result when the limit of h approaches 0 of this function, or I should say what that limit is as h approaches 0, we end up with 2x plus 2 as our formula for the slope. Therefore, we can say that the slope when x is equal to 1 this time would be equal to 2 times 1 plus 2, which in this case is 4. So I don't know what the picture of this graph looks like, but evidently when x is equal to 1, the slope at that particular curve is equal to 4. Now I'm using some notation here, and I've used some notation back here just to imply that we're making some substitutions. I just do that to make you familiar with lots of different ways that we can indicate substitutions. In class, we'll discuss which particular notation seems to be more appropriate or more common to use. Now, evaluating this limit, there are a couple different ways that we can approach this. The tendency might be to imagine what happens as x approaches 0 and either use a table of data or kind of interpret analytically what might be happening here. Although I'd be willing to expand this numerator a little bit and see if something algebraically occurs. I notice that 1/3 is being utilized here, and it'll be essentially cubed in the active expansion. And then I also have this minus 1/3 cubed as well. So I'm hoping that after I expand that, those coefficients, or constants I should say, will eliminate one another, and then we'll be left with some terms that contain a common factor of h. And if I can factor in h from the numerator and denominator, I think we've got a candidate for direct substitution. So I'm just going to make a note here that this is the limit as h approaches 0 of... Now I could write this expression 3 times over and multiply them together, but instead what I'm going to opt to do is use binomial expansion, and this relies on Pascal's triangle. So if you're not familiar with what I'm showing here in just a second, I would consider searching this expression and looking up the words Pascal's triangle as well, and see if you can follow along with what I'm doing here. This binomial can be expanded 3 times by using the coefficients from Pascal's triangle. So this component here, and I'm going to put it in its own brackets for a moment, would end up being 1/3 cubed plus 3 times 1/3 squared times h plus 3 times 1/3 times h squared plus 1 times h cubed. So that's the expansion of this. I don't have to FOIL or distribute 3 times. And from that, I'll subtract 1/3 cubed. And all of that is to be divided by h. Well, now hopefully you can see exactly what I thought would happen. We've got a 1/3 here that's going to subtract 1/3 here. I should say 1/3 cubed. Now all we have to do is simplify the expression. So the limit as h approaches 0 of this new expression is going to be true. Well, I've got 1/3 squared, that's 1/9, and 3 times 1/9 is 1/3. So I have 1/3 h plus, 3 times 1/3 is just 1. So I've got 1/3 h plus h squared plus h cubed, all divided by h. And if we recognize that h is a common factor from the denominator and can take one of the factors from each of these each of these terms in the numerator, we can do that. You might also recognize, as I illustrated before, that we can factor the numerator by the common factor h and state that h times 1/3 plus h squared can be divided by h. Now we see the common factors that cancel, perhaps a little bit more clearly. And finally, we can state that the original problem's limit is equivalent to the limit as h approaches 0 of simply 1/3 plus h squared. Now we can perform direct substitution, and as we do so, this expression approaches 0, this one approaches 0 as well, and I think we can claim that the limit of the original expression is quite simply just 1/3. Now here again, if we had a calculator, if this question showed up on the calculator permitted portion, we may use a graph, we may not. It would be kind of hard to trace the results with the graph due to the accuracy of the decimals that we see there. But I might consider using a table of data. So we might consider what x and f of x look like, or I should say what this would look like if I'd substitute h into the function. And I'd pick h values that are getting really close to 0, both from the left, so negative 0.001, etc., and also from the right, so 0.001, again as we approach 0, and then just start investigating what's happening to the function results as we get closer and closer to 0. That might be sufficient for you to make this estimate. Now, to be perfectly honest, though, the algebra method led us to a direct result, whereas the table method and graphing method would lead us to a decimal value, which we might interpret as this result, but we do have to be somewhat careful there. So now we move on to interpreting limits based on graphs. We have a floor function here, which we talked a little bit about in class. We didn't spend a whole lot of time talking about it, but at least we did discuss it a little bit. This time we're approaching 1 from the right of this function, and we'd like to know what its limit is. Well, fortunately, we have a nice picture here, and we'd be asking ourselves, if our target is 1 and we approach from the right because of this plus symbol here, I think it becomes fairly clear to note that the function value, the function, in this case h, evaluated at w, is approaching 0 as we tend from the right. So we would just simply answer with 0 there. Coming from the left, however, as we approach an x value of 0, x value of 1, as we approach an x value of 1, we see that our function value is tending towards -1. It's sitting flat on -1. But from the right, we would say 0. On this one, we've got a piecewise function, which, when written by itself, could be a bit confusing. Since we have a graph to look at, I think it's pretty straightforward. We are approaching +2 from the left. So as we approach this discontinuity from the left, I think it's fair to say that the limit is equal to 1. The function value is remaining steady at 1 as we approach this x value of 2 from the left. Now, if we didn't have a picture to deal with and we're only interpreting a limit based on this piecewise function, that's okay as well. We just have to be careful here. Take note of the limit instructions. We are approaching 2 from the left, so that means that we're using r values in this case that are smaller than 2. And if we're using r values that are smaller than 2, then we must use this function, and this isn't even part of the function to consider. If all of our r values are less than 2 but approaching 2, then the function result is always equal to 1. And that further supports our claim that the limit as r approaches 2 from the left is equal to 1. And here we have another limit question. This time we're evaluating a limit as x approaches 2. So we can consider what happens from the left and from the right, but I might also suggest using algebra here. We know that the limit as x approaches 2 of the original function would be equivalent to the limit as x approaches 2 of the factored function. So I'm going to try factoring first. This looks like something that can factor nicely. And let's see here, if I have a standard trinomial, two products that multiply to make -2 are 2 and 1, that also add or subtract to make -1, as this coefficient here, I think does require a -2 and a +1 more specifically. So now this factor can cancel, and we're left stating that the limit of the original equation is equal to the limit as x approaches 2 of this equation, 1 over x plus 1. And at this point, since there's no violation for substituting the value of 2 here, I would use direct substitution. And we can claim now that the limit is equal to 1/3, 1 over 2 plus 1. Now, had these questions shown up on a calculator permitted portion, you might end up generating a graph and using the trace feature. Or if I give you a picture of the function and indicate where the holes in the graph are, as I've done here, then you can also interpret the limit by simply looking at the graph. Hopefully you do recognize that there is an issue here. We cannot substitute the number 3 into this expression. It ends up creating a 0 in the numerator and denominator. So that's what created this removable discontinuity, or the hole that's here. So, as I start looking at this a little bit more closely, I'm more nervous because I can't quite interpret what the function value at that position is. I can see that the graph is tending towards a single position from both the left and the right, but I don't quite know what that is. So I think factoring is going to be necessary after all. So let's go ahead and recall that we do need to include this limit notation in order to be consistent. We have a minus sign and x minus 3 in the numerator. We have the denominator that I suspect can be factored. Let's go with x minus 3 and x plus 1. That looks like it'll FOIL back together to make this expression. Those will cancel. And we have the limit as x approaches 3 of -1 over x plus 1. And with direct substitution, we end up with -1 over 4. So that looks okay to me. It does look like the x value is a little bit closer to 0 than it was a half. And to make the claim that it's -1/4, I'm okay with that. I would be ready to move on. Now here's a limit that we can clearly interpret by looking at the graph. Find the limit as x approaches -1 of this particular function. Well, as x approaches -1, which sits right here on the x-axis, as we approach it from the left, it looks like the function is rapidly increasing, so we would say that the limit is equal to infinity. Now 17 behaves similarly in that as we approach 1, we end up getting a 0 in our denominator, and it's a non-removable discontinuity. So that implies that we are creating an asymptote. When we create an asymptote, we can start thinking about this just mentally here. If I can substitute the number 1 in this numerator, we see how this numerator is going to approach the number 3, because 3 times 1 is 3. And if we substitute the number 1 in this denominator, we see that it approaches 0, and that's where our problem lies. However, if we use a number that is slightly smaller than 1, if we're approaching 1 from the left, we're talking about a value that's slightly smaller than 1. Any number that is almost 1 but slightly smaller than 1 does produce a 0, but that 0 value is slightly smaller than 1. So we might say that this is a negative 0. We had talked about that in class, and we agreed that this isn't really a formal description, but it's a good way to interpret the limit behavior here. Well, 3 divided by 0 we know is some sort of infinity, and as it turns out, a 3 divided by negative 0 should be a negative infinity, but we've also got this negative sign that's hanging out front here. So if you want to imagine this as negative 3 divided by negative 0, I would end up arguing that the limit in this case should be positive infinity. In number 19, I would argue that we can make a similar thought, or claim rather. As we approach negative 2 in this numerator, there's no problem there. Negative 2 squared is going to tend towards 4. And as we start substituting in numbers that are close to negative 2 here, we will approach 0. Well, that's the problem. 4 can't be divided by 0. It's undefined. But if we choose a number that's slightly smaller than negative 2, well, now we're dealing with a number that's like 1.9 or 1.99. And if I had multiplied 2 times that value, something slightly smaller than 2, then we get a component that's a little bit less than 4. A number a little bit less than, negative 4. I had a mishap with my recording device here, but I think I'm caught back up now. But anyway, the 2 times a number that's slightly smaller than 2 produces a value that's slightly smaller than negative 4. And it's important not to get too hung up here. If I'm looking at number 4 on a number line, a number that's slightly smaller than 4 would be something like negative 4.1 or 4.01 or something like that. So if I had the negative 4 point something plus 4, well, that approaches 0, but it's slightly negative. So when I take the constant value 4 and divide it by 0, I get some sort of infinity. And as it turns out here, we have a positive 4 divided by a negative 0. And I would make the claim that this limit is equal to negative infinity. Now you'd be able to confirm or refute some of your claims that don't include a limit, or that don't include a graph by going to a calculator and checking them with a graph, but that may not be available on the test. So it is important to establish your limits without the use of a calculator. Also, you'll notice that all of these limits are pretty straightforward. They're polynomials or rational functions. We're not getting into any of those wild limits that we saw in our homework. Remember, we've only got a finite amount of time for this test, and I want to test your understanding of the big concepts rather than all of the heavy algebra that went into lots of our homework. Besides, you had an entire week or more to complete your homework. You've only got a little bit less than 60 minutes to take this test. So I don't want to burden you with heavy amounts of algebra. Now, to finish the video out, let's recall that there are 3 checkpoints for continuity. The first checkpoint is that the function has to be defined at a, our target value. The limit also has to exist as x approaches a. And then finally, the data from number 1 and number 2, so checkpoint 1 and checkpoint 2 must agree, or they must be equivalent. And if we can identify failures at any one of these points, then we can determine where there's a point of discontinuity. If I look at number 21, I would argue that this graph illustrates a continuous function. And I know that because, number 1, any point along this shape is defined. We can calculate f of a either by looking at the graph or by using the piecewise function. Every input, I should say, will produce an output. Even at this cusp right here, it is well defined by this component of our piecewise function. So it passes all of number 1. Number 2, we also have limits that always agree for every point that we could consider within this domain. Even this guy right here, The limit does exist. As we approach from the left and to the right, the limits agree, so therefore the limit itself exists. And as it turns out too, every limit, and again, I think it'd be appropriate to focus on this point because that's the one anomaly of the group. But if we look at this particular function value here, which is equal to 0, and the limit, which is equal to 0, those two agree. So for number 21, I would say that the entire graph is continuous. So all points are continuous, however you spell it. There we go. Close enough. For 22, we have this anomaly that exists right here, and you might recognize that this is a discontinuity. We know that the function is defined. It passes checkpoint 1. We would like for the function to be equivalent to this data point right here on the rest of the graph, but it's not. It is well defined elsewhere, though, so we're okay with checkpoint 1. The problem with this particular, it passes checkpoint 2. I almost said that it didn't, but it does pass checkpoint 2 because the limit of this particular function does exist. But it actually fails checkpoint 3 because you'll notice that the limit leads us to believe that the function value should be 2. So the behavior of the function as x approaches -1 is 2, but the function value itself, when x is equal to -1, is equal to 4. So this fails checkpoint number 3 at the position where x is equal to -1. Other than that, however, all other points on the graph would indicate a continuous function. So for 23 and 24, I'd ask that you complete that on your own. Hopefully you recognize that in each of these cases there will be 2 x values that produce discontinuities, and I'd like for you to explain why. Tell me which checkpoints they fail, and again, identify both of those. Now my battery's running low, and the time is getting quite lengthy on this review, so I'll go ahead and stop it here, and I'll produce another video as needed. Thanks for watching.